plan that was going to take 4 years to remove the fuel. I mean, my God, we won World War II in less time than it's going to take them to defuel that reactor.
Well, you know, as Arnie points out, this pool is already showing signs of failure. But, you know, in the United States, we have more room than they have in Japan. They have a lot of people in a small space. So when they designed that nuclear power plant, they didn't have a place on the ground to put the spent fuel or the waiting fuel in water in a pool on the ground. So this pool is over 100 feet above the ground on top of the building. Now, you got to realize that nuclear metal, you know, is incredibly dense and incredibly heavy, and the amount of weight up there that's being held on the racks, you know, holding all these rods up there, is an enormous amount of tonnage. And the way that they have to remove that fuel, no one really knows how to do yet, because you can't ever let it get exposed to air or it bursts into flame. So they're going to have to somehow remove the racks of fuel rods, keep them immersed with a crane lifting this megatonnage of fuel rods somehow in water to get it down to somewhere that they think they can do something with. No one has ever done anything like this before. No one really knows how to do it yet. So that's why they're saying, well, it's going to take 4 years because we don't know how to do it yet.
Sounds like we should call David Copperfield or something. He's probably got an idea about how you pull off a contortion like that. Is that something that that they even think about in the design stage of these plants, Arnie? Is that something that they take into consideration? Let's put the pool above ground. Is that, I mean...
Well, there's 23 plants in the U.S. that have the same problem, but the other 80 do not. So we learned this first generation plant, putting that fuel way up in the air like that was a mistake. And the remaining 80 plants in the U.S., after we built those 23, have that fuel pool much lower and in a much more protected spot. And it's actually worse in the United States, because the Japanese only put 7 or 8 years of nuclear fuel in their fuel pool. And in the States, our fuel pools have more than 30 years of nuclear fuel in the pool. So if there were to be a problem in a U.S. pool, it would release even more radiation than we're afraid will come out of Fukushima.
Well, you know, it's interesting. We're sliding the U.S. story in here in a bit, and I think a lot of people here in California, guys, it's a beautiful day, we're in summer, you know, the gardens are going, and it's really easy to get distracted at the beach or something, but there was 2 weeks ago a really interesting short little AP clip that I came across that was talking about, and that's actually why I wrote you, Arnie, and was wondering if you'd be available to talk, because there was this little clip I'd seen about 1,200 cooling rods being failing at San Onofre, and that's where I think we should go maybe with the conversation. And we do have a video clip, a little experiment that you just ran down there on site. And why don't you tell us just real briefly how you set the clip up, and then we'll go to the clip and share that with our viewers.
Well, I was hired by Friends of the Earth to figure out why these tubes inside the steam generator were failing. And you can see these very complicated engineering drawings, and frankly, I thought we needed a better way of explaining what a U-tube steam generator looked like. So we put this video together on the beach, and we simulated U-tubes, and I got to show how they were banging into each other and causing the problems that is happening at San Onofre today.
Awesome. Well, let's go to that clip, and we'll come right back to you as soon as that's run.
Hi, I'm Arnie Gunderson from Fairwinds, and today I'm at the San Onofre nuclear plant that's in the background. San Onofre is presently shut down. It has steam generator leaks. And I wanted to give this demonstration today to talk about what it is exactly that a steam generator does and how they can leak. Well, this blue thing around me represents the key component inside the steam generator, and it's called the tube sheath. It's 2 feet thick, solid steel, and 13 feet wide. So that's just about the shape and size of what I'm standing inside of. Now this would be a solid piece of steel before it's fabricated. Weighs about 100 tons. It's enormous. Now, first thing they do is they drill holes into this tube sheet. They drilled 9,700 holes on this side and 9,700 holes on this side. What happens then is when they put the steam generator together, hot water comes from the nuclear reactor, and that's symbolized by this orange pipe. So hot water would go through that. It's actually 32 inches in diameter, and 250,000 gallons every minute comes in. It comes in the bottom and goes up through these tubes, crosses over, and comes down on this side. Now where I'm standing is not the radioactive side. I'm standing on the non-radioactive side. Radioactive water is inside these, and hot steam and hot water is where I'm standing. Now, if you notice, these things are shaped like U's. That's why it's called a U-tube steam generator. The pipes come in, cross over, and come back in the shape of a U. Now, we've modeled up 3 tubes here. In fact, there would be 9,700 tubes on this side, and each one would cross over into 9,700 tubes on this side. When San Onofre decided to rebuild their steam generators, they made a design change, and I believe that it's that design change that's causing the tubes to fail inside. Right where I'm standing, right in the middle of this tube sheet, down below was a massive pillar. It was called a stay cylinder. San Onofre decided to get rid of that massive pillar down below to cram more tubes into the steam generator. Instead of 9,300, they got 9,700 tubes. By removing the place right below me, more tubes meant they could get more heat out and more electricity out. But it also changed the flow inside the nuclear steam generator. What's happening in San Onofre now is that these tubes are vibrating, and they're colliding with the pipes, with the pieces of metal that are designed to keep them separated. The vibrating...
Arnie, we're watching this clip that you just shot down at San Onofre, and we're getting to a really critical point in it where you're talking about how the vibrating of these tubes probably punctured and has caused sort of a laser-like cutting reaction to occur. I'm wondering, while we're bringing that clip back together, perhaps we're wondering if you could explain a little bit more about what your theory is on how the damage was caused by that single pipe, ruptured pipe, and how that impacted the 1,300 coils that all were taken offline.
Well, actually, although Edison went after me vociferously, I was proven right. The reports we wrote that are up on the Fairwinds website were proven right just last week by the Nuclear Regulatory Commission. What happened was this. Edison didn't build the same steam generator that was there. They really tried to juice it up, and in the process, they screwed it up. They created a spot, like a sweet spot inside the all these tubes that was pure steam, and that no one ever planned on that happening. And in that pure steam, the tubes were banging together and damaging each other. Now, one happened to leak, but quite a few others were severely damaged by all this banging. Now, the NRC said that Edison could hear the tubes banging with something called the loose parts monitor and ignored it for 10 months. So there's lots of problems here that the Nuclear Regulatory Commission isn't addressing. How the computer programs were ever qualified to do this kind of design. They had a 400% error.